Good morning. So, to position my work in the field of edu HiPC, let me just give you the general anatomy of any course. So we have concepts, examples, and assignments. And of course, when we are teaching parallel programming, we add threads to all of these components. And there's given a set of concepts and examples. There's a variety of assignments you can have. Given a set of concepts, you can have a variety of examples. And you can also have a variety of concepts taught in a course on concurrency. And there's two reasons to have variety. One is variety for the sake of variety, to add spice to your life. And the other is because you have addressed certain fundamental issues differently. So what I'm going to talk about today is how, in a course that I've developed for concurrency, how the issues I faced and how I handle them differently. So the first issue that arises, and something we talked about in the training workshop yesterday, is that do you teach concurrency in a course that is based on concurrency? And so operating system and concurrent algorithms, their basis is concurrency. You can't imagine having operating systems or concurrent algorithms not address concurrency. Or do you take courses that have traditionally not taught concurrency and add concurrency to it? Okay? And not adding it in an ad hoc way, adding it in an integrative way, and I'm going to say an amplifying integrative way, which means that by adding concurrency, you better understand the concepts that are not concurrent also. So if you've somehow figured out how to do sorting concurrently, then I think you understand sequential sorting a little better too. You realize what parts can go independently. Okay? So if you're doing the latter approach, you have to figure out which course you're going to add concurrency to. CS0 typically means some course with a visual programming language, which is not that powerful. CS1 means a powerful programming language, and you maybe teach them for loops and arrays, and you take them till there and no more. CS2 has many flavors. Often it means data structures, and it can also mean object-oriented programming. And in our department, a lot of students come with loops and arrays. So the first required course is a course on object-oriented programming. I had previously taught concurrency in an advanced operating system course. So the ultimate challenge for me was to add concurrency to this first course that we teach. Okay. So the next question is, are you going to teach concurrency in a declarative fashion where you just tell the system what you want? How are you going to get into the how? Okay. So we saw in the training workshop yesterday, OpenMP gives you high-level declarative mechanisms. And here's the same code being done procedurally. Okay. So high level is, declarative is high level, procedural is flexible. And if you're talking of Java like we are, you have to talk about all kinds of concepts here that have to do with implementation. Okay. And you might want to shy away from the hard work in an introductory course. But the approach I took was the procedural one. Why? Because this course is on object-oriented programming, and by adding these concepts in there, we get more objects, which reinforces the concept of object-oriented programming. Okay. So object-oriented programming and modularity don't make very much sense if all you have is one main method. So the more the objects, the more you amplify the whole concepts. So you have to then go and motivate students. Why are we doing concurrency? And the classic reason is you take an algorithm like sorting without concurrency, and then you add concurrency and it has better performance. And the programming became a little harder because you had to address concurrency. Okay, so the ease of programming reduced, performance increased. There's actually a dual reason for adding concurrency too. And there's a paper in the book that has been CDAC Center, I guess. Cedar Center, sorry, too many C's. Okay, Cedar Center, sorry, I'm influenced by your talk before the talk. So, and this is this person in a CS0 course is trying to teach students how to animate a boy moving a ball. Okay? And what he does is he creates two threads that exchange, one for the ball, one for the boy, and these threads communicate with each other through messages. And the reason why he did it, I believe, is because programming became easier. If you were to do the same problem without threads, the programming would be harder than if you did it with threads. And when you do it with threads, I'm going to argue that the performance reduced. Because even though we have internally two threads, there's really only one independent activity. Each time the ball moves, the boy moves too. So there's a lot of message passing and context switching going on, and so the performance is going to reduce. So what's really happening here is that you're using the operating system's context switching capability to reduce your problem. Otherwise, you'd have to do the context switching yourself. Okay. So there is this reason that you might add concurrency not for performance but for ease of programming, and in fact you might lose performance. But ideally, and this is the approach we targeted, if you have say two boys moving two balls, now you can get both ease of programming and performance, and so the examples we chose belong to this class. Okay. So these goals make our approach different from what the literature I've read. Okay, and the question then was, how do we? This is the what. How do we? What's the how? Okay. And one luxury we did not have, since because of these goals, was that we couldn't just take classic examples like, find if a number is prime or not, or multiply a bunch of numbers, or multiply matrices. We had to come up with compelling examples. So what's the theme for our driving problems? And the main theme, the key insight we had was that physical objects in motion provide a good basis for two reasons. A, they give you analogies to explain what concurrency means. Okay, this is important if you're not going to implement the threads yourself. And second, if you're doing object-oriented programming, it makes sense to take physical objects and simulate them. Okay, that's why the first object-oriented language was invented. So I'm going to argue that the simulations of these physical objects help motivate and visualize concurrency abstractions of thread synchronization and thread coordination. Okay, so in the time remaining, I'm going to expand on these 2 points. Okay. And the idea of visualizing algorithms to sort of show how they work is not new. If you haven't seen it, you should look at sorting out sorting video that really shows sorting at work. And in all these animation systems, the student develops just the algorithm, and some external system creates the animator for that algorithm. In our world, the students create the object and its animator, consistent with creating as many objects as you can in a course on object-oriented programming. So that's a difference, but the effect should be similar. Yeah, and the effect is now on concurrency rather than on sorting or some other data structure algorithm. So let me go in first, expand on the first point, that how do physical objects in motion give you analogies? So I do tell students that, look, when you have multiple threads, you have multiple stacks, and you have multiple programming counters, counters can go independently. And the analogy here is, when I'm overworked, I wish, when my computer's overworked, I wish I had more processors. When I'm overworked, I wish I had more heads and more hands. So this is sort of the analogy here. Properly, you have to also talk about interleaving when you don't have enough processors for the threads. So here you have 3 threads and 2 processors, and one thread is not active while other threads are interleaving. Here's my analogy for interleaving and concurrency, which is a little more interesting. So 2 hands serving 3 balls is like 2 cores serving 3 threads, and when ball is in the air, the other balls can be served. So while a thread is waiting for a user input or sleeping, other threads can be served. So I've shown you an analogy for threads. Okay, we'll deal with synchronization and thread coordination later. Let's now go into how I can motivate and visualize concurrency abstractions of threads. Okay, so the one example I use continuously is a space shuttle, okay? And it begins at a certain position where it ended up. So in the animation, we know where the ending position of the shuttle is, and we can execute a command that says animate from origin. It goes to the origin and then animates its path first in the y direction, then in the x direction till it comes back to its original path. Okay, that's a simple example. You have, of course, your main class. You have the shuttle. We don't add the animation to the shuttle. Separation of concerns. We want to keep these things separate. And we have a shuttle animator. And animate from origin, the main method calls animate from origin, which goes and repeatedly calls set shuttle in the plotted shuttle. Okay? So that's the structure with a single thread. So multiple threads, well, you have multiple shuttles, and we can have multiple animators too. So the same set of objects as before, but we've instantiated them now twice. And then you have to have a runnable or a shuttle animation command for each of them in Java. And that runnable is accessed by another kind of object, thread object, which is started now by the main thread. And so this is a more complicated thread. Again, complicated is good because we're teaching object-oriented programming. So we're emphasizing the fact that there is a bunch of objects that are doing different things and talking to each other. And you don't have to rely on performance results to show that there's concurrency. You see the two shuttles going literally concurrently. Okay? And so that's my argument that you see concurrency visually here. Okay, so that's the point I just. Let's go and talk about concurrency analogy for synchronization. Okay, so let's take two cars. Sharing a road is like sharing a computer in these two cars, and if you're in different lanes, then you're sharing different resources. So you don't have to worry about synchronization. For the same lane, you're using the same resource, so you have to worry about synchronization. You have to worry about not hitting the car in front of you, and more important, as we do in India, driving in the opposite direction. Okay, so that's the analogy. How to go and show this in an actual example. So the separate lane scenario is that we have separate shuttles, separate animators, separate command objects, separate threads, no interference. We don't have to worry about synchronization. What if we had two animators, okay, a backseat driver and a front seat driver, trying to go and move the same object? Interesting things can happen. And I ask students, what do you think will happen? And which you see right here. So let's start this. Okay, so you see the tug of war going on between the two animators. And so they see the need for synchronization and the fact that it's shared resource. And then, of course, I teach them about the synchronized method in Java, critical section, and explain what it means. And we do the same problem with synchronized methods. And this time they see that when this time first animator gets the synchronized method first, and then second animator gets it. So things are done serially. So we've seen how to go and both motivate synchronization and explain synchronization using physical objects. Now comes the ultimate challenge, thread coordination. And here's the example to illustrate that. So I go to an interactive object I built, and I say start animation, but the shuttle just waits. I do another shuttle and waits, and I say proceed, and the first waiting shuttle goes. And then I do proceed again, and the second shuttle goes. Okay? So you see here thread coordination, that there's somebody waiting, there's somebody signaling for the threads to go. And how does the thread wait for an event? Just use notify and wait. And if you know anything about Java or wait and notify, you know that these have to be executed in synchronized methods because they access a common queue. And I tell them all about that, and that's why I use the word proceed and wait for proceed, because these are methods that are built on top of notify and wait that just add the synchronized method. Okay. And analogy is that you have a relay race, so the next runner is waiting for the previous runner to give the baton. Okay, so and then let's go and look at notify all. So again, I go and make the first shuttle wait, start the second shuttle waits, then I do proceed all, and they all get notified. So this is again showing you exactly how the notify all method works in Java, okay? Or at least see its effects. And the analogy again is we saw the proceed and wait to proceed, and a policeman allowing a bunch of cars to start, or a running coordinator allowing a bunch of people to start the race corresponds to a proceed. Okay, so it just mirrors what they've seen in real life. So everyone waiting proceeds, one person proceeds, and now sort of it demystifies a lot of these abstractions. Okay, and again, proceed all is just a method, the synchronized method that calls notify all. And I also show them in this object I created, the interactive object that you did proceed all and proceed on. I also show the queues. So now when two shuttles are waiting, the queue has both the threads. I press proceed. One of the threads one of the movement thread starts moving, and a thread gets released and it starts moving the shuttle. And it will proceed a second time, and both elements get removed from the queue. And in proceed all, again we have two threads waiting. I do proceed all, and both elements, both threads get default. Okay, so what kind of assignments did we give? I'm a big fan. I don't know how many of you know about Monty Python and the Holy Grail. Some of you Americans here might. So my students love this thing, and they actually build a simulation of the knights and the bridge scene. So this is the guard, and these are the four knights. And I take liberties with the bridge scene. So at one point, the guard starts clapping, and the knights have to clap in unison. Okay, that's where I get the synchronization. And the synchronization in the knights is hardwired, that before they move the arms in, they wait, then they move the arms out, they wait, and they just need signaling or proceed. And what I had them do, since I'm very ambitious, I had them actually write a command language to execute commands, procedures interactively. So here they're defining a procedure called beat, and the vocabulary is the objects in the simulation. So it says the beat procedure should call guard's arm in, which is a predefined method, then do proceed all, give a signal, then sleep for 500 so that you can see that hands clapping, then call guard arms out, then do proceed all again to give another signal, and sleep 200. Okay? And then define beats as calling beat method 5 times. Okay, so they actually write an interpreter for this for loop here and the procedure. And then there's also this method thread beats, where you don't make the caller wait, but you call beats in a new thread rather than just calling it in your current thread. Okay. Let me just show you this thing working. So at some point I go and say, so you see these guys are going now. I don't know if they saw that or not, but they were going in synchronization. So I've been teaching this, I think, I actually forget when I started first teaching. But I looked at my records, and I know I taught it in 2012. So in 2012, I met Pooja from IIT Kanpur, who had just invented Piazza at that time. So I went and saw my Piazza data, and I know I have a course in 2012 with threads. Okay? And like Preeti, I'm going to use the Piazza data to sort of, so I didn't have all these data collected in the hope that I'm going to present this paper someday. Okay? So what I'm going to do is, and I initially was very ambitious. I made the assignments on concurrency required. And then I added more things to the course, added quizzes, so I made them optional. And whenever you make course assignments optional, people are more excited. And they have an option. So I'm going to just show you not aggregate statistics like Preeti did. What I did was I just looked at the first course and I searched for threads, and I found the first sort of post that had some interaction. And here you see the classic problem you run into when you're doing synchronization. The student says, look, my thread is just blocked. It's hung. And these are the steps I've taken to figure out what's going on, and I know that it's hung there. And if you read this, and you don't have time to do this, but you read this carefully, you see that there's a lot of sophisticated language being used for somebody who's teaching the first program. Okay? And the real problem here, which I had to figure out after reading this message multiple times and the answer multiple times, was they called wait to proceed in a synchronized method. So it just grabbed the synchronized method block and waited, so nobody else could go and come into and execute the synchronized method while this guy was waiting. So the system just somebody much smarter than me, a student, Danny, who I remember was a freshman. He figured that out and said, "Are you sure you're doing proceed? Wait in the right method." And then he explains exactly how it should be working, and that's allowed, by the way. They can always give the algorithms in English. Okay, so identifies the problem right. So he says, "Oh, that helped." But guess what? I've got another problem. And now he's used to a crutch, right? So he says he's hoping Dan will reply back again. But Dan doesn't. So he has to think, and he actually figures out the answer correctly, that he was actually, he tries successfully to get help, and he was calling proceed instead of proceed on, and he said, "I'm really sorry for having, sorry, there's a typo here, for doing such a stupid mistake." So to me, this shows that points got across. I mean, if, in a course like this, when they're talking this language, I'm pretty happy. And I'm going to show you statistics here from 2012 and 2018. 2018, the assignments were optional. And A8 and A9 were the assignments before the concurrency assignments. A10, they got threads and they started recursive descent parsing. A11, they added some new commands and they did synchronized method. And A12, they did wait for proceed and proceed all, and they did the full command language. And the main work was in the command language. Okay? And these are the submissions. I didn't look at the points. That in 2012, 70 people got till A9, and 3 people couldn't make it to A10, A11, and A12. And it might have been threads, but I suspect it was the parsing. And in 2018, 59 people got to A9, and then the really ambitious ones decided to do the 3 extra credit assignments, which were all packed now. And 45 did A10, they got threads, 33 did A11, and 28 did A12. So whether they got stuck or whether they ran out of time, I don't know. Most of this work happened during Thanksgiving break. And so, some people might have had a life. So the point I want to make here is that it has been possible to teach low-level abstractions for thread creation and synchronization coordination in using simulation of physical objects that amplify O concepts in a CS2 course requiring knowledge of arrays and loops. That's all, which is taken by many freshmen. And my lectures, my example code, my tests, I have a lot of tests for these, hands-on exercises are all on the web. And that's where I like.